I'm Mark Lefsrud, and I'm going to be giving a quick overview kind of the world of controlled environment challenges that we see moving forward. I'll touch on some of my own research, but also research of other individuals. I wanted to put up this slide because these are the factors that ultimately we have to care about. So we've talked about a bunch of these ones through the sessions up to this point. I'm the past chair of a group known as the NCR 101 or NCERA 101 group. It's a controlled environment working group that's sponsored by the United States Department of Agriculture. And as such, we're trying to develop, not standards, we don't work on that directly, but we try to develop methodologies and patterns and recommendations for people to do growing. So this is a list of all the different factors that we consider to be important. There may be other ones that need to be added in the future. One of the big claims of the NCR 101 was that we were the ones that came up with the idea of PAR. You will see later that maybe we defined it incorrectly, but that's a bit of a larger challenge. It at least allows us to start talking about things on the same level. So one of the challenges that I've been seeing for the last 20 years that I've been working in this field is that when we started in this area, most people talk different languages. So some people would talk about lumens, foot candles, watts, micromoles, and all these things were being used interchangeably. And so one of our goals has been to try to actually unify so that we can at least compare apples to at least oranges so that we're not comparing something totally different on this. And so you can walk your way through these things. So we have the energy factors, the water factors, atmospheric factors, earth or substrate, as well as the structure and the plant. The part that we have the poorest understanding by far is the plant, even though that's the system that we're actually trying to allow to grow. Our understanding of what it does and how it behaves is actually quite poor. If we go through energy and light, I'll show that I think we have a poor understanding of that. Water we're okay with. I won't say we're great. Atmosphere we're reasonably good. Substrate, still up for debate whether or not we're quite where we need to be as a whole. But back to the plant, ultimately, I argue with a lot of plant growers, specifically because they keep telling me about how they have to improve the quality of the soil. And from my perspective, I'm trying to improve the quality of the plant. Soil is just a mechanism for me to transfer the nutrients and the water and everything that is required for the plant. So if I'm slowly destroying the soil, it doesn't bother me because I'm trying to make my plant healthy. If you're trying to grow healthy soil, then don't put plants in it, is ultimately what the solution is for that. So challenges that we have with the plants. Ultimately, specifically in the world of cannabis, we have a large challenge because it's been illegal for so long that it's not even really considered a crop in its true sense. It is a plant and it falls in a lot of categories under that place, but plant breeder rights and legal jurisdiction on who owns what is still up for debate. So if you have a variety or a strain or a chemophore, whatever you want to call it, these aren't protected. If I grab one of those seeds, it's now mine. And so it doesn't fall under any legal category, at least from a Canadian perspective, and most places around the world fall into that same place. Unlike if you're growing wheat, where there is an actual genetic mapping that you can do, and you can identify the phenotypes that are being present in this, and as such, it can actually belong to somebody so that we can allow for the breeding and the operation of this. And this is one of the large challenges that the government is going to have to start to challenge or put forward across both Canada and the United States and around the world. And then we get into the whole breeding side. Cannabis is the same as all other plants. It is a plant. And they have a bit of genetic variation that happens, and they like to mutate and modify themselves. We've seen many plants that you'll have two branches, and one branch is one chemotype, and the other branch is a different chemotype. So you can get that with apples, where we do grafting and we see these differences. But we can see those also with the marijuana or the cannabis strains also. We also have the other regulatory challenges and the actual operational challenges. So operation, diseases, energy and electricity, which we've been chatting about for the last couple of days here, the economics and the policy, and ultimately the end products. So what is it that we're actually after on these things? If we look at it from an environmental standpoint, the light, water, atmosphere, everything that I've talked about has to be determined. How do we play with this? And one of the things that you'll see in this slide, which is why I wanted to highlight that, is most people are used to growing plants with an overhead light system. But because of LEDs and their lower temperature, there's nothing that says that we have to do that. We can put lights below or in your canopy or from the side. We follow the principles of having overhead lights because the lights were really hot. They were bright, and we said, well, we're just going to mimic the sun and going to stick them up in the roof and shine it down. Plants really don't care where the photons come from. As long as a photon is coming to it, it can come from the bottom or from the side or from the top, and it doesn't matter if it comes from an electrical lighting system or from a solar system. The plant does not care what a photon is. Once it is released from the reaction and a photon is released, the plant will utilize it as it sees fit. And then finally, we have our production challenges, and this is an area where the engineers, as well as a few others, have to step up, because right now, with the amount of production that we have out there, we don't have enough labor. Most people don't want to go around and do pruning continuously within their life. Some people enjoy it, it's relaxing, but as a whole, this is going to be highly labor intensive, and we just don't have enough labor for this. So we have to figure out how to automate a lot of this stuff. And so I'm expecting we'll start pushing these things down where human actually doesn't touch the cannabis plant the moment the seed is put into the ground until it comes out the back end. We might have observational, or there'll be computer systems for tracking this, but there won't be any human intervention actually physically touching any of these things. Everything will be automated. And then as you go through the list, the drying, trimming, grinding, and extraction, all these things have to be automated. A lot of these things have come from the underground market, so some of them are quite good, some of them are not. And one of the big challenges we're going to have is actually trying to figure out which ones are acceptable and which ones aren't, and the policies that need to be put forward. And this session and the groups that are involved with this have at least been making these efforts to try to put forward some of these, but there's still a lot of disinformation out there. I hear a lot of growers telling me what they're planning on doing, and I just shake my head. I'm in awe that they'd be willing to do this to a plant. And I'll discuss a few of those as we work our way through. So this is my laboratory. I'll talk about almost everything that's in that loop there. So a lot of pretty pictures, and that's why I like to hold it up there. But as a quick plug for myself, the kale plant's in the center, which is what started my whole PhD world on this. So I cared about kale before anyone else did for some reason. Little did I know that other people would care about it, because when I started, people would say, what the heck is kale? And now you can actually buy it as a salad at McDonald's, which I find even more surreal that we've gone to that state. So this is kind of an overview of what my laboratory does, but it's also an overview of the parts that I'm going to talk about. So the parts that are bolded are how I'm going to walk my way through this. So I'll talk about the history a little bit, and then the research areas that we have. I do work in the post-harvest, the processing, and the monitoring systems out of this, and I can talk for a really long period of time on those things. You'll see a little bit as I'm working my way through this, but predominantly the last half will be on LEDs, and the first half will be on other projects. So the start of controlled environment basically started, well, if you want to go all the way back to the beginning, was probably the Babylonians period that actually started it with the hanging garden type systems. And there has been other efforts along the way to try to bring it inside. During the Second World War, there was a big push for this as we were doing island hopping during the Pacific campaign. And so trying to figure out how to grow plants in places that normally don't grow a lot of plants. So if you're on a deserted island, how do you pull this off? After a while, it was the Air Force predominantly that was in control of that. Russia did a lot of work with the biosystems out of this, and then NASA kind of took it on, because if we're ever going to leave Earth or Earth's orbit, we have to be able to produce food for us to actually stay in those locations. So the first one is the cells project, part of the larger breadboard program that they had down there. There's been a lot of them that has been tied together. They deal with a very, very small chamber type system, so usually at best 1 meter by 1 meter. And in a lot of cases, we have to worry about all these different control factors within a very, very tight space. So one of the jokes that I've always said is that if you give me enough energy, I can grow any plant in a thimble. And it's not a joke. We can do it. It just takes a lot of energy to try to control this. The larger your buffer, the less energy you need. And then the second picture is a plug for University of Arizona, Gene Giacomelli, which was my master's advisor. And so they ended up building a growth chamber that went to the South Pole. The part that's fun about this is ultimately the food okay. Ultimately, the people have an affinity for plants, and people love plants. So that little area that you see in front, so this area in front right here is actually just 2 seats, and it's one of the most popular places at the South Pole. And so people have to book it weeks in advance so that they can sit there and do work or have a supper there so that they can stare at the plants. You are in the middle of a snowy glacier for all intents and purposes, and so this is kind of highlighted through. We kind of tell stories about amongst ourselves that if you were going to be isolated from the rest of the world for the rest of your life, what's the one organism you take with you? And for me, it would be a plant, probably kale, ultimately. I know I don't like kale that much, but it's at least one that I know that will survive. And it has its own quirkiness that makes it interesting. It's not one that's more passive like lettuce, which doesn't do very much. It's more of a feisty type plant. So if you're walking through, this is a bunch of the NASA stuff. So if you want to hang out with anybody, they're kind of fun projects here. I worked for Orbitech for a year, and so when I arrived, this was the biomass production system. It flew on the space shuttle for a couple missions. But the work that we were doing actually evolved into the veggie plant system, so that's that system. So there's 2 systems that are sitting on the space station right now, and so it allows the astronauts to have lettuce. One of the mandates that came about through this is the astronauts now mandate that all future human spaceflight using NASA technology has to have the ability to grow plants, which from my perspective is quite cool, because it used to be that slightly people cared, and now people care a lot. One of the fun stories is that when they tasted the lettuce the first time, they said it was some of the best tasting lettuce, or the best tasting lettuce they'd ever had in their life. About a year later, they grew kale, and they asked what the kale tasted like, and they said it tasted like kale. So, and then the further technology that's happened here is the APH, so the advanced plant habitat. So these chambers are about 1.5 by 1.5 by 1.5, roughly in size. And so they're fairly small, and the full control system for controlling, regulating everything, light, temperature, CO2, you name it, is all occurring in that spot on the side here, and that's the actual chamber. So we can do fairly good work in very controlled spaces. The reason why I highlight this is usually the people who are pushing the technology is this side, but because of cannabis and the deep pockets that have been arrived because of that, some of the work is now flowing back the other direction. So there's this ebb and flow that's happening. In the world of geology, oil field is the one that controls the technology. NASA uses it to go explore Mars, but then sometimes Mars technology can come back and help the oil industry. That's from my experience working for a year in the oil industry. Let's see here. Oh, one too many. So I worked on a project called Urban Barns. It was an indoor plant growth system. This was when they were fully up and running. Our biggest claim to fame was that we were growing lettuce in under kosher conditions, so no insects on it. And so we actually were functional economically. Our last quarter, we made 20 bucks, and then they went defunct thereafter. But they were profitable for one quarter, I can say, which I thought was exciting. Okay, so into my type of research. So we did that work to try to make it economically viable. And I realized that as an academic, ultimately I suck at that. My ideas are usually too cutting edge, too far out there, and doesn't always make it to the economic side. I still think at some point they're all going to reach that point, but I'm not going to ever be the one that will see that. It's kind of a freeing experience once you realize that the ideas you have aren't probably going to happen within your own lifetime, because it means I can push on a lot of crazy things. One of the big challenges that we were talking about was how do we actually deal with the light and between controlled environments and greenhouse type environments. And ultimately I ended up building this greenhouse for the northern space. And so it actually has a wall that can actually move itself up and down. So in the summertime, it keeps it open unless it starts getting too hot, and then it will close itself up. In the wintertime, when there's no light, it closes itself up. So you can actually use this as a regulatory, temperature regulatory and light regulatory system. It also has some light, some temperature management systems that also come in on these things, but you can actually see the plants are growing reasonably happy right on this side. And you can actually start playing with these different factors. So I'm hoping as we start moving down some of this lower carbon footprint type, that we actually start to evolve technologies to store heat that's being produced in the daytime and able to use that in the evening or in the cooler period. And so it's one of the challenges that we ultimately have. I've also done work on tropical greenhouses, so trying to develop cooling systems. So here's a fairly standard tropical greenhouse, has the top roof with a sawtooth design, air comes out and flows out through the top there. I ended up developing a system to actually cause cooling on this. Typically we use fans. I cheated, if I can call it that, and I added a misting system into the middle of it, so it actually causes a coolant loop to actually start to form naturally within the side. So it's a natural convection loop system using just water. Out of this, the advantage of it is I can chill down the greenhouse to about 5 degrees cooler than outside ambient temperatures, and it allows you to actually maintain this. So there's a lot of technology. The reason why I'm highlighting this is, one, because I did it, and I think it's kind of cool technology. But the second thing is that I find that there's a lot of growers, both in the tomato industry as well as the cannabis, that are resistant to trying new ideas. And so sometimes you have to set aside 10% of your greenhouse or your growth area and just try new technology and see if it works for you. I won't say all of them work, but there is places that we need to do this. If you want to be the big, huge Canopy or Aurora or such like that, fair enough, but they should have their own branch that are doing these technologies to try to test some of these parts. I've also worked on watering and control systems. And so as part of one of these, we actually developed an automated monitoring system. So it was basically a camera that stared at a fruit. So as the fruit grew, you can actually see the fruit in the center right here. So it has a web camera sitting right there, the fruit sitting in the middle here, and we're just taking pictures of the fruit as it slowly continues to grow. People have done this work in the past, but they usually use tensometers or calipers to try to measure them. We measured it about every couple seconds as it was growing. And the part that's kind of fun about this is we can actually see the growth pattern as it moves itself up. So from 55 millimeters as it moves up to 55.5, and you can slowly see. So we have a resolution of fractions of a millimeter. So this is like basically 1/32 of an inch kind of side. So very, very fine changes that can occur on this. And so in some cases, we can track this as normal, healthy growth. In this case, we actually are in drought conditions. We're not pumping enough water into it. And the case that we found in one situation is my student actually was doing a test. He came back and I started looking at the data and I go, something's wrong with your system. And he goes, no, everything's good. We did the test, everything's fine. I'm like, no. So about 10 minutes later, I came back and I looked at it and I go, the plant's still shrinking. The fruit's still shrinking in size. Something's wrong. And so he walked back out there and realized that he had unplugged the pump. So we missed one watering cycle. So it was fast enough to watch one missed watering cycle, which is literally in our system, it was a 1 hour period. And drought conditions usually at best is 3 hours, typically 6 to 12 hours is when most people will observe this. So the technology ability of using web cameras, which is fairly basic, allowed us to be able to monitor missing one watering cycle or missing one system that so if the nozzle was plugged, we can actually start to track these things. One of the funky things that we found about this, and I have no good explanation for this, is we started seeing this oscillation. So as the plant was growing or the fruit was growing, it was oscillating up and down, up and down. And it's not a very big oscillation. This is like less than a 1/32 of an inch, but it's a very small oscillation. And it wasn't making sense why this was happening. So we zoomed in on one of these things, and it basically was telling us that as I'm watering my tomato fruit, for some reason it shrinks, which makes no sense whatsoever. If you add water, things should expand. The plant's uptaking the water and should go through an expansion. And the reason why I'm highlighting this is it tells me that we know nothing about plants. We know that the plants are there, we know that they're growing, and they're going to continue to grow. If I backtrack on that, you can see that they're continuing to grow. But there's all this data buried in that we just call noise, which isn't actually noise. It's useful information. We're just too stupid to understand what it is. And through technology, AI, and all these other things, maybe we'll start to figure out what the plant is trying to tell us. They speak a language, we just suck at understanding what that is. But we will slowly start to figure this thing out. So other fun projects that I've worked on, and I am continuing to work on, so this is a porous concrete type structure. So we actually we're not using Portland cement, we're using actually a steel slag out of it, and so I'm growing grass on it. The part that's kind of fun about it is it's a pH between 8 to 10 pH. Everybody says that you should grow between 5.5 and 6.5. Our research is showing that you can grow up to 8 without any problem. It doesn't mean that we have to change our nutrient ratios. So on the next one, you can see that our ratios are being changed. And so a standard rock wool cube, which is sitting right around that 6.5, normal is where it starts, and our 3 different porous concrete cubes here. And then I had to go to a double nutrient solution to get the same kind of size out of it. The difference is that this is quite an elongated leaf and elongated stem system, while this is more dwarf. So we can actually start to control by these things. And so this is a calcium effect, as well as a bit of a nutrient effect that actually starts to play on this. I think it has a lot of other applications more than just the controlled environment space, but it allows us to actually start to push these boundaries. So working on carbon dioxide enrichment. We can also do CO2 enrichment. And so one of our projects is using biomass as a heating system. We heard yesterday most people have to compost or landfill most of the residues from the cannabis world. If we can start doing anaerobic digestion, that'd be good. In my cases, I'm just wanting to burn the stuff, and then I could recycle them almost directly. I know I'm producing a lot of CO2 through the combustion, but ultimately my goal is, why can't I use that same CO2 over and over again to actually grow the plant? So theoretically, you can be carbon zero at best. Actually, you could go negative in some cases if you can manage this. But there's a lot of regulatory requirements for them to actually get to this point. And I know in the island of Montreal, they've actually got to the point where they actually tell us we're not supposed to be burning any wood because it causes too much emissions. So then I developed this technology, which is basically pulls all particles out of the air. So it's basically a great big electrostatic precipitator type system that can pull stuff out. And as such, it's quite good at this, and I'm hopeful that the government at some point will allow me to start to use this, but it's still in its earlier stages. So hopefully in the next couple of years it will start to reach itself out. So I'm going to jump into light now, which is ultimately what my main baby is and what I work on predominantly. We talked about these, basically the different wavelengths and the different spectrum that comes about from these. As you see here, this is our big solar output, and then we have LEDs, and everybody says LEDs, if it's blue, one of my standard statements. But you can see that we have a full width half medium, which is actually fairly wide, 20 nanometers, which actually means in some cases we can get up to 150 nanometer widths. And so this causes a lot of issues because ultimately we're averaging over the 150 and getting the plant response as we move across that. So we're not playing with hyper narrow wavelengths, we're dealing with slightly narrow wavelengths. And so what's the impact if we try to go even more narrow out of these things? And so that's what a lot of my research is on. You saw this slide before, and so the whole wavelength that we have, we talk about the green gap space here, lower productivity, but ultimate, because of our phosphorus-coated systems that we have, we can actually produce a bunch of light within that. My gap that I talked about last time is right in that 680 to 700, seems to be the place. Most people don't seem to care about it, which is good, but me as a researcher, hey, if people don't care about it, it's usually a good place to be. And so trying to figure out how we can actually see what the responses of these are. We know that the technology has been slowly improving, so I stole this from Morgan Patterson, with his permission, of course. And so he's done a lot of work on how much is the efficacy and the output of these, and so we're slowly improving on efficiency of the lights. And so you can see blue is slowly creeping up to be the maximum output. Red systems also are improving. He added amber because I've been ranting about it for quite a while. So it's still a long ways up, but it does have the theoretical capability of being just as efficient as everything else. I might be dead before this happens, but it will be getting up to that point at some place there. And then you can see the other kind of lights and their efficiency that come about this. The reason why this matters is ultimately we're trying to fit different pegs into different holes, and they aren't always a perfect fit. So we know that efficiency is one of the things we're chasing, but ultimately we also have to be aware of how the plants actually respond to a lot of these things. So our standard system out that we use is our basically metal halide HPS system. Fluorescent is still a good system. We just don't get an exceedingly high light output out of most traditional fluorescent systems. White LEDs, which are basically the same thing, we are getting a better system. So I usually recommend to people to stay in that place, and LEDs are used for other secondary applications. So, and I'll explain why I make that statement. So here's our standard McCree curve that everybody's familiar with, and then there's the whole I can't even remember, Hog-Wingen system that he also did it as a mapping system. We have a bunch of older technology that they used for these things. This was done back in the 1970s before LEDs came along. And it's kind of been the standard on how we're going to grow. So, and most people looked at this chlorophyll pigment. So we have our chlorophyll A is the dark coloration here, and our chlorophyll B is the lighter green coloration. And we looked at it and say, well, they kind of line up with this peak here, and they kind of line up with this peak here. But if we look across at the bottom here, they don't really line up on that shoulder, and this edge doesn't seem to line up. So how come we have fairly good efficiencies when we play here, which is good because it lines up with chlorophyll A, but then we play in this area and it still grows plants exceedingly well. But then I come down into the green, don't get quite as good a results. So when I was a student, I looked at this and goes, we don't understand the system. And everybody goes, no, 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 it's well explained. Pigments cause photosynthesis. Well, maybe not. As I look at the different kind of systems, I can choose LEDs. So one of the first LEDs that people played with was actually that 680 LED. Does not work well at growing plants. You get long spindly plants. Nobody likes them. Almost destroyed the LED industry initially. 10 years later, then we ended up with our 660s, 640s started coming in. People started being quite positive to this. Low pressure sodium. Few tests were done on that. Most people have never really grown larger scale with that. But it falls in that nice little peak area where that is. So why don't we do more work with that? The short answer is no one has. If we look at metal halide, fairly broad spectrum across it, a lot more blue, but still has a fair bit in that amber coloration, lacking in the red, as opposed to HPS, which is very amber driven on this, a little bit of blue, and a bit more red than we actually see in the metal halide. Most people like HPS. Bruce Bugbee and the crew at Utah have done a lot of work trying to figure out what these different sensors are, or the different systems within the plant-based. So this was a paper of his in Nature that was published, what, it was 2 years ago or so. And so you can actually see these are the standard LEDs that I've shown you before. And then we actually have all the pigments that are within plants and the actual responses of the human eye systems also. And with this, it makes it look like there's a lot of sensors that are present on this, and they have the ability to actually monitor these different wavelengths. Some of them are very slight. So if I'm at very dim light conditions, I get a fairly strong response out of the plant. If I'm not sitting at dim light conditions, I go to bright light conditions, I swamp out that, and I actually don't get any of the responses at that point. And then human eye response, and then our different plant responses, and overlaying them. You can see that the amber kind of follows that. The HPS follows the amber spot that's right there. And so these are kind of some of the conclusions that were made. And so one of the things that I've been pushing for quite a period of time is the fact that within the cannabis world, we've had this idea that red light is very good for flowering and blue light is very good for vegetative growth. It doesn't happen. I'm sorry. I've done a lot of literature review. I've done a lot of my own studies on this. I've done a lot of studies on this, both on cannabis as well as other plants. Cannabis is a plant. It behaves like all other plants. What that is up for debate, but it is a plant. And so as such, in most of our cases, we find red light drives photosynthesis, and blue light is used as a stress response induction system. So it's the sensory system, which causes the plant to be aware that it should start to flower. And so there's different mechanisms. If you have purely red, it will still flower, but it's because of a saturation of energy that starts occurring, and the plant goes, okay, I'm just happy, fat enough that I can now start to go to this flowering period, but I can use my blue for actually induction of these flowering quicker. Bruce Bugbee has also published this paper, which just came out actually a few days ago, which is based on the Emerson effect. So up to this point, PAR has been between 400 and 700. He came along and says, well, if I start adding my far red light into this, I can actually induce better yield. And so if I measure it based purely on a PAR response, I basically am increasing my yield in this lettuce under about 400 micromoles of light. And so if I take it and change my PAR to 750, now it starts behaving like a normal curve. The challenge that happens with this is if I give only far red, my plants will not grow. So Emerson effect is this combined effect of other wavelengths of light with the far red light. If I provide just far red light, I'm not going to get a positive response. I've tried it. It doesn't work. So you have to have the two light systems. So if you're using it as kind of an induction to say, let's get my plants woken up by giving it some far red, you're getting a little bit of red because of the tails that happen on these things. But ultimately, it's not completely driven by that system. And it's saying that basically some of our units of measure might be incorrect, which makes for a lot of people to pull out their hair because we've been staying with 400 to 700 of the system. So work that I've been working on, which I think is kind of fun, is we've been looking at really high intensity type light systems and different locations and how intense we can get up to. So in this case, we're getting up to about 1,400 micromoles of light, and we're looking at what the growth rate was at different wavelengths. So we're looking at our amber, we're looking at our red, and we're looking at our blue. So this is on tomato, which is one of our model plants out of this. And you can see blue light seems to be non-responsive. So there's a bit of a yield increase as I start to increase, and then it seems to flatline out of this. These were small plants. I understand it's not full growth out of this one, but my red light actually gets a nice bell curve. So anything over 1,000 for red basically is starting to cause negative growth. So it's actually causing light saturation on the plant, and so going above that isn't beneficial. If I go for amber light, pure amber light, then it actually seems to maximize at about that 800, and then it starts to drop off after that. If I start combining these, then it starts doing a whole bunch of funky stuff, and we get those kind of linear responses that we're expecting to see out of that. So these are the plants, so different morphology out of all of them. You can actually see amber, though, causes some photo bleaching systems on this, and so we have to understand why those are happening. If I do the same tests on lettuce, I can see amber causes my maximum growth rate, red out of the system, and then my combined as my blue, so slightly better responses for my lettuce relative to my other pigments, my other wavelengths that are working on this. The part that I find kind of fun is that depending on how you grow them, so this is varying intensities. I have very smaller plants to my large plants, but then I get my whole anthocyanin and pigment accumulation. So I can get into very, very dark colorations, high anthocyanin accumulation. So that's why I make the statement that blue induces a lot of photopigments, as well as in other parts of it. And then if I jump ahead here to my amber, you can see that I actually are getting in that bleaching type system, so I'm actually causing destruction, but under the combined coloration, I'm actually getting, depending on what my ratio is, I can start changing a lot of the phytochemicals that are present within this. And so here's just a quick summary of them, which I think is kind of fun. As kind of the last part that I have for the last 3 minutes before the questions, ultimately we've done some work on amber wavelengths and just started to filter these. So we actually took different wavelengths, so a 595 and just put a notch filter in it, and then we did a 615 and did an end filter on this to try to actually control what happens if I shift my wavelength slightly within this space. And this is the resultant out of it. So 595, fairly normal looking to it, compact plant by going to a 603, so just literally taking a notch out of it. And then if I do the same, basically overlaying the other wavelengths out of that, I end up with this. Intensity is the exact same. Wavelength is shifted, in some cases, 3 to 5 nanometers. And that caused that large of a differential of the response of how the plants were. So back to that statement I said, we don't understand what plants are up to here. And so we're trying to figure out how these are. So when somebody says, I tested it at my location and I got this response, but I tested it at a different location and I got a different response, it's possible it was a temperature differential, which caused a difference in your, I'm not saying temperatures and growth, I'm saying temperature of your bulb caused a 2 to 3 nanometer shift of the wave output, and you're getting that response. And we have to start to figure out how these shifts are happening. And from a policy standpoint, if we're saying we're chasing always the most efficient, it might not be the most efficient for the plant. And then you can see our fresh weight and our photosynthetic rates. So I do a lot of photosynthetic measurement on this, and you can see these two are quite similar, but they result in a different result. And very high photosynthetic rates here, but not very good growth rates. And so we need to try to separate those things. So main takeaways of this: science has a poor understanding of plants, and base of many of the assumptions are incorrect. If you want to come to NCR 101, I'll rip a few more things apart at that point. Not willing to do it quite here. And we need to have a better understanding of how plants evolve into these environments. It doesn't mean that we don't have a good ability to grow the plants. We just don't have a good explanation on why it's doing it. Individual wavelengths can be both positive, negative, and neutral. And so in some cases, we find them very detrimental, but in some cases, very beneficial. And then ultimately, I'm a big supporter of amber, which, giving plugs to companies that use broad spectrum lights, I'm a fan of them. So. If you are interested in any of these things, I am part of almost all of these groups, well, with the exception of ASHRAE. So NCR 101, which does a lot of standards, ASAB, which did the plug before, so thank you. As well as we're also trying to, well, DLC also is a group. And then SEEDS, we're trying to work on trying to set up standards for controlled environment across the board. And if anybody's interested in that, there's a few of us here that actually are on that committee. And so trying to figure out what the standard should be or how we can actually monitor and work these things forward. And then all my acknowledgements for this was from the main people that have worked on these set of slides with me, and then everybody that's in my lab. So it's a fairly large lab. And I'm willing to take some questions for, I think I have a couple minutes at best. Pardon? It's known as Darth Vader. It was an asteroid that landed near my father's farm. So if you want to go see it, it's at the University of Alberta. I also love that little island there. So there's 6 sheep that hang out on a coast of Scotland. And so it's the epitome of controlled environment because they can't go anywhere. They bring a boat in, and then they have to go grab them before they jump in the ocean and drown because they're full of wool at that point. So you bring 2 boats in, a few dogs, and then try to herd them together and get them off the island once a year. So that's her. Thank you.
Yeah. I thank you very much, Dr. Lefsrud. I would appreciate a little more recommendations on the policy front. You kind of dipped into that direction.
So the one challenge that we have, and so I'm in Montreal, which is part of Quebec, and we have really cheap electricity rates there. Hovers between, I've heard as low as like 3.2 cents per kilowatt hour to as high as 5. Ontario goes above that, obviously. And we're probably not going to have much restrictions on power usage. So here in California or Massachusetts, when they put on a restriction of some power, I'm actually quite happy about it because it means Montreal will export to you guys, is what I'm after. And so the challenge that we have ultimately is that some of this technology for the amber sucks at efficacy. And you saw that on the slides. So if we're putting in barriers, we're going to be testing them elsewhere, which might be good because it's not a bleeding edge. It's just you're waiting for the new technologies to come along. But there has to be a mechanism set up in place to allow for new technologies that have the potential of being even better down the road. And until we get to that point, it's hard to make that full final recommendation. I like the idea of a framework. And so the SEEDS group that I'm working with, we're wanting to do a ranking system. So high, medium, or low, or bronze, silver, gold, however you want to rank them, good, better, best type system. So that, and if it's just power, I think water, electricity for light, HVAC systems are 3 separate systems, and they should all be kind of grouped together, but also allowed to be worked independent. So if you want to focus on a high efficiency LED, but don't want to have the other stuff, you should be allowed that. And that's one of the challenges that's happening with the current policy, is that people will cheat on one system versus the other. But I think all of them have to be considered in the end. And so that's my recommendation.
Doctor, for a given intensity of light, does the evapotranspiration change by spectrum?
Yeah, we're working a lot on that. So we can change stomata opening and closure by doing wavelength selection on that. So green light predominantly will close it, but we still grow quite a happy, healthy plant. And part of the challenge is also leaf temperature. So depending on the wavelength you're using, can control leaf temperature and stomata opening. And we're just at the early stages of having a good understanding of how these things are interplaying with each other. To be perfectly honest, we don't know why stomata open or close. And we have ideas. We know that wavelengths can do this. We know temperature can do it. There's a bunch of factors, but there has to be some underlying mechanisms that will do this. And we don't have a strong understanding of this. So we can control that, and we should, but it doesn't mean that I'd say that you should be betting the farm on that mechanism. Okay.
Hi, Mark. Thanks for the presentation. On the amber LED, did you look into the efficacy on the plants of using the amber LEDs itself versus phosphorus-converted blue LEDs? And
yeah, so we have done both. The phosphorus coated has quite a high efficiency out of it, or efficacy out of it. So they're comparable to almost every other system that's out there. They play with the HPS as efficiency. If you're doing narrow spectrum, which is what those last wavelengths were, where we're filtering them down, they suck. But I personally think they have a greater potential of changing the industry than the broad spectrum does. The challenge is that I can't say with certainty how that's going to play out. Okay, thank you.
Thank you, Mark.